Hi everybody, welcome back to the channel. In this video we're going to take a look at our last family of functions, which is logarithms, and we're going to see how to find derivatives of logs. So there's actually a couple of different types of logs we're going to look at, and we're just going to go ahead and jump right in. The first one is what happens when you have a function like y equals a log with just a generic base b of x, and then the second one has a specific base that we're hopefully very familiar with, the natural log of x. And just as a reminder, the natural log is just the same as regular log, just the only difference is instead of having a generic base of b or a base of 10 or a different one, it specifically has a base of e. We usually don't write that little base of e, but that's what that means. So both of these are ones we can take a look at, and they actually behave very similarly. They actually also behave pretty similarly to when we talked about exponential functions. That probably shouldn't surprise you because we know that exponential functions and logarithmic functions are very much related. They're not the same thing, but they're very much related. Okay, and with the first one, what we're going to see, and I don't know, I'll just tell you up front what we get for the derivative, and then we'll look at where does that come from and why does that work. But the first one, when we take the derivative, we're going to get something like 1 over x, and then there's an extra natural log of b down on the bottom. And for the second one, y prime is just going to look like 1 over x. And just like when we talked about exponentials before, you really could write this second one as using the formula from the first one. You would have an extra natural log on the bottom, but there's a natural log of e, which is the base, and the natural log of e is just 1, so you don't need to include that. So we don't include that. It's just 1 over x. And so that's a fairly nice result as a derivative, but we'll see kind of where does this come from. So let's go ahead and start with the first function, where we have something like y equals the log base b of x. And hopefully you remember some logarithm properties, because some of those are going to show up in this video today. But one of the things you might remember is that with logarithms, you can change the form from being in a log form to being in an exponential form. So the way to do that, what that would look like, is you can change this to looking like b raised to the y power equals x. And so now we have an equation that means exactly the same thing, but now it doesn't have a logarithm in it. And what we could do now is we're trying to find y prime, and so we could actually go and bring this back to talking about exponential functions or exponentials and be able to take derivatives of exponentials. So for example, we could take the derivative of both sides, d over dx of b to the y. Remember, b is just a constant. D over dx of x. And we know how to take the derivative of an exponential. So the idea here is we don't know how to be able to take a derivative of a log. So let's turn it back into something that we do know about, and then we'll kind of work with it from there, and hopefully end up with being able to find y prime. So d over dx, the derivative on the left side, hopefully you remember that one, the derivative of an exponential function. If you have a base of b instead of a base of e, the derivative looks like b to the y times the natural log of b. And that's what you would get as your derivative if it was like a b to the x. But since there's a y up in the exponent, just like we did when we talked about implicit differentiation in the last video, y is like a y of x. So really there's a chain rule going on there. And I used this phrase a few times in the last video. I said that anytime you take the derivative of something with a y in it, you also need a dy dx. That shows up there, and that's the derivative of the inside function just being y of x. And then on the right side, that's pretty straightforward. The derivative of x is just 1. Okay, so our goal here is to get dy dx by itself and to basically solve for y prime here. So you can go ahead and take the b to the y and the natural log of b and move those over to the other side. You get something like 1 over b to the y times the natural log of b. But then what was y again? If you remember what y was at the beginning, y came from up here. Y was the log base b of x. So another way to rewrite this, because we don't want to have y in our answer, if we can avoid it, if we can bring it back to x's instead of y's, that would be ideal. So 1 over, let's see, b to the y is b raised to the power of log base b of x times the natural log of b. Okay, so this is what dy dx is. Now, again, I said I hope you remember your log rules from past classes because those are going to show up. One way those log rules show up is that when you have a base of b and a log with a base of b, the exponential and the log undo each other there, and so this piece right there, you actually just get x. Okay, you actually just get x from that. So as our answer, we have dy dx equals 1 over x times the natural log of b. Okay, so that's what our derivative looks like. And again, b is just whatever your base is. It's just a constant here. And I want to encourage you to think back to when we talked about the derivatives of exponentials. When we talked about the derivative of an exponential, which actually shows up kind of on the bottom left here, we took the derivative of b to the y and we got b to the y times the natural log of b. There was an extra natural log of b showing up in that derivative. Well, in this derivative with logs, there's also an extra natural log of b showing up on the bottom because we don't know what that base b is, and the different bases that you could have for b change your answer, change the problem that you have. So we got to account for b in there somehow. Okay, the proof for the natural log is almost exactly the same. We'll look at that. That'll be really quick as well. So suppose you have a function y equals the natural log of x. And remember, this just means you have a base of e. So another way to rewrite this equation is to write it as e to the y equals x. We don't know off the top of our head, or we haven't looked at this yet, we don't know what the derivative of a natural log is, so we got to bring it back to an exponential equation. But now that we have an exponential, go ahead and do what we did before, almost exactly the same steps here. Take the derivative of both sides with respect to x over here, so d over dx, like this. And then on the left side, this is going to be e to the y, because e is its own derivative. And so e to the y, but then y is your input variable there. And so you still need a dy dx. Remember, anytime you take a derivative with respect, anytime you take the derivative of something with a y in it, you need a dy dx. And then you still just get 1 on the right side. Great, solve for dy dx. Okay, move the e to the y over to the other side, and so you get dy dx is 1 over e to the y. But oh yeah, what's y again? That was the original natural log of x. Okay, so dy dx is equal to 1 over e to the natural log of x. And you might remember that e, just like with the last one with a different base, e and the natural log, because the natural log has a base of e, those undo each other there, and you're just left over with something like dy dx equals 1 over x. Okay, so go ahead and add these to your derivative rules in your notes. These are good ones to refer back to, but again, we're going to see these enough that you should memorize these really quickly. And just like with exponential functions, the natural log is going to show up maybe a little bit more. That's a really good one for you to know just off the top of your head. And that one doesn't involve that extra natural log of b. A little more friendly, shows up a little bit more often, but it's really good to have the other one there for you as well. What happens when you have a base of b? So to summarize, the derivative of a log base b of x is equal to 1 over x times the natural log of b. Pick up that extra natural log of b on the bottom. And the derivative of a natural log of x is equal to 1 over x. Okay. Now, one interesting thing to note about this is that if you remember, logs are only supposed to have a positive input. You may remember what a log function looks like. The graph looks something like this. And so when you talk about the domain of this thing, the domain is all real numbers that are positive. In other words, you can't use 0, you can't use negative numbers, only positive values, okay? But if x is a negative number, then you could have something like the natural log of a negative x, and then the domain would be negative numbers because you'd have a negative negative inside. Okay, but let's say you have something like the derivative of the natural log of negative x like this. Okay, so basically that function would look something like this one over here to the left. And let's say this is your function and you want to be able to find the derivative of that. This actually involves a chain rule where the natural log is the outside function and the negative x on the inside is like your g as your inside function. And so you can take the derivative of this whole thing using the chain rule that we had. And again, all these rules like chain rule, product rule, quotient rule, all these things, these are going to show up all the time. And we're not going to be told what rule we have. We just got to keep an eye out for it. So the way we would handle this is take the derivative of the outside function, which that's the derivative of a natural log. That's 1 over something, okay, whatever's inside of your natural log, that's what goes on the bottom. So it's 1 over a negative x, but then you need times the derivative. So this part, by the way, is your f prime of g, okay? And then you need g prime, which is the derivative of the inside, which is the derivative of a negative x. Well, that's just -1. And so the negative here with the -1 cancels with the -1 on the bottom. You actually also, in this case, get 1 over x as your answer there as well. And so an interesting case here, we can consider what happens when you have the natural log of x or the natural log of negative x. They both end up giving you the same answer. So we can take it just one step further and be a little bit more specific. Instead of just saying that the natural log of x is equal to 1 over x, we can say the natural log of the absolute value of x, because that kind of includes an extra function. It includes kind of another half of the puzzle there. If you have a negative x value, the derivative of that would also be equal to 1 over x as well. Same kind of an idea. Okay, so as I said, all the same rules still apply. We can still use a chain rule with natural logs and all this kind of stuff. So let's take a look at one example here. Let's say we have a function like y equals the natural log of the sine of x squared. Okay, and we want to know what y prime looks like. Just a little practice here. Again, your outside function is the natural log. You can think about the derivative of that outside function is 1 over something. But hopefully it's pretty clear here that there's going to be a chain rule. And so what goes on the bottom of the fraction is a sine of x squared. Remember, you just plug in whatever was the original input. Then multiply by the derivative of the next innermost function because of the chain rule in here. So multiply by the derivative of a sine, which is a cosine of x squared, okay? And now there's actually 3 layers here, not just 2. So now we need the derivative of that last function on the inside, so times 2x at the end. And another way you can write this, by the way, is you can write it as cosine of x squared over a sine of x squared, and then there's still times a 2x. So sometimes when you have natural logs and you're taking derivatives, because you get a 1 over piece and then there's other stuff multiplied that's going to go on the top, you can actually make things kind of, you can actually simplify things a bit and make it look a little bit nicer. So cosine of x squared divided by sine of x squared is actually a cotangent of x squared and then times 2x, or you could put the 2x in front, that's fine too. But you can actually simplify the way that that answer looks a bit by combining the different functions that you have together.